Okay. Good afternoon, everyone. Welcome to the Asia Solar Energy for Climate Changes Conference, a platform dedicated to harnessing the power of renewable energy in our fight against climate change. The conference is organized by Carbon Care InnoLab. My name is Xixian, and I'm honored to be the moderator for this insightful panel discussion. The session today, we will focus on the topic about optimizing solar energy performance in extreme weather conditions, particularly the role of the tech solutions. Today, we have three honorable speakers. So I just have a very quick introduction of their name, and according to the alphabetical order of their name. We have Miss Akansha Sakanali, who she is the India lead on the Energy Access Explorer under the World Resources Institute. And then the second, we have Dr. Masaru Yarami. He is the Associate Professor, Division of Public Policy and Division of Environment and Sustainability, the Hong Kong University of Science and Technology. And the third one, first speaker is Mr. Upa Patachachi. He is the Senior Technical Lead in Asia Clean Energy Partners. In case you want more detail about their background, you can go to the website, ASECC website. They have more detail about their background and expertise. Without further delay, I will first of all invite Dr. Yarami to share his presentation. Dr. Yarami, please.
Okay, thank you very much. My name is Masaru Yarime. Currently, I'm working at the Division of Public Policy and the Division of Environment and Sustainability at the Hong Kong University of Science and Technology. Today, I'm going to talk about some of the key opportunities and challenges in facilitating smart distributed energy systems in Asia, and we would like to discuss some implications for public policy and governance. I think now increasingly we are trying to use data-driven innovation for tackling various challenges in this urban context. So we have a lot of digital technologies introduced to buildings and also the transportation, and also energy, which is increasingly important in tackling the climate change. There are a lot of opportunities identified for tackling some of the climate change issues and also other sustainability issues, especially in the area of energy. We have a lot of potential available for reducing CO2 emissions by introducing renewable energy sources and also efficient energy usage. So for these purposes, the smart technologies can play a very important role for facilitating all this renewable energy introduction and also efficiency improvement. And also, as the theme of this session, we need to introduce the resilient energy systems against all the disasters, including hurricanes, typhoons, earthquakes, and extreme weather events. So we also need to think about really the resilience of energy systems. So that's why I think we really need to think about the digital technologies, which are especially important in the context of Asia, where there are a lot of the disasters and also extreme weathers are really affecting our life. So we have a lot of potential for mitigating climate change and also adapting to climate change or resilience to climate change in digitized energy systems. So one domain which is quite important in this area is to try to introduce the distributed energy systems. So as you can see, centralized system is a more traditional way of providing energy, where you can see some very large energy the power plants. And then we have a kind of one directional energy supply from these large plants. But increasingly, we can see a potential in decentralized systems. And also then we have distributed energy systems where there are a lot of microgrids connected. And also we can explore the peer-to-peer energy exchanges between households. So I think there are a lot of forms of implementing distributed energy systems, where you can see rooftop solar is one, and also microgrids, where localized grids can operate more independently for the main grid. And also we can see a potential in community renewable energy, where the locally owned and operated energy systems can work together among all the members and households in the community. And then also we can see increasingly the battery energy storage systems introduced to the grid system and also to distributed energy systems. So there are a lot of advantages of distributed energy systems, including proximity to the customer and also high energy efficiency, and also particularly in tackling climate change, we can introduce clean energy sources by facilitating the more flexible and also resilient energy systems. So that will be very important for tackling climate change. So I've been working with my colleagues for the past years to try to explore the opportunities and challenges in distributed energy systems, particularly based upon blockchain. So as you can see here in this system, you can see the households. They produce energy by putting solar panel on the rooftop, and then you can also install the batteries. And also increasingly, we can see a potential for introducing and installing the EVs integrated to this system, so that then the households can become also a producer while also being a consumer of energy. So then we can connect all the households through peer-to-peer network, so that we can exchange energy through households. So that would be really distributed energy systems with peer-to-peer energy exchange based on blockchain. So here we can see a lot of opportunities, so that we can see a kind of internet of value, in the sense that we can have a kind of a lot of benefits of decentralization through this system. Like we can see kind of increased resilience when something happens and affected the main grid, but we can still maintain energy system if the energy system is more distributed. And then also we can facilitate the introduction of solar panels and also EVs put together, and then we can have a very flexible and resilient energy systems. And especially now we see a potential of introducing AI for transactions and those smart contracts in this kind of distributed energy systems, so that somehow automatically we can see all the transactions of buying, selling, and scheduling of all this exchange of energies between different actors. So we have examined all the challenges with regard to technological, economic, social, environmental, and institutional aspects of distributed energy systems. So as you can see, there are many challenges remaining. And particularly we see kind of implementation and the testing and the learning from a project would be quite important in tackling these challenges, as I just mentioned. So there's a case in Tokyo about these distributed energy systems based upon blockchain. So you can see the households are physically connected so that they really try to exchange energies. So I think these kind of experiments and trials will be very important for learning what are really the key obstacles and challenges in implementing this kind of energy systems. We also made a lot of interviews with experts in this area with regard to this blockchain-based distributed energy systems. And then we came up with some of the really the key institutional challenges in smart distributed energy systems, including the regulatory complexity, which means that we also need to deal with the license issue for selling electricity, which would be normally the case for households. Also, we need to think about smart meters, because this is also critical for measuring and verifying all the data about energy exchanges. And then also we need to think about some of the cost issues like the surcharges for network fee and taxation for really exchanging and storing energy in the grid system. And then we also found that it's really critical to deal with the data governance, including data ownership and privacy, and also data sovereignty issue. So in that sense, there are a lot of legal uncertainties. For example, the standardization is still missing, and also cryptocurrency issue. And also we need to deal with the incumbent interest in the sense that usually we have a lot of the existing energy players, which tend to be really large and also have their vested interest. So how to manage all these the institutional issues would be quite important. So then that I just like to mention finally about the smart meters, because in the end that we really need to integrate solars with the smart technology so that we can facilitate more flexible and resilient energy systems. So we have also made some study about advanced metering infrastructure. And then that we see what we found is that soft technologies are actually quite important in facilitating AMI architecture. So as you can see, a lot of processes are involved in actually installing the smart meter systems so that we don't need to address this challenge. So in the case of solar, we see a kind of cost reduction can be possible by accumulating all the expenses and also increasing the production. But in the case of smart meters, then we really need to address the soft cost issue as a major constraint for the future introduction. And especially we see compared with the hardware technologies, how to manage and how to facilitate cost reduction in soft technologies is not so clear and also easy. So in that sense, I'd like to address the three implications for policy. Standardization, we need to harmonize all these specifications and protocols. And also we need to encourage more competition in smart meter and other technologies supply markets. And also we need to facilitate more integration, considering all the local specificities. So that's really the future for Asia. So I'd like to emphasize that we really need to proceed to promote solar integrated with the smart technologies so that we can facilitate more flexible and resilient energy systems in the future. So this is the end. Thank you very much.
Okay, thanks you very much, Dr. Jeremy. Okay, then we will have more discussion after all speakers present their material. Okay, so the next one I would like to invite Mr. Upa Bhattacharjee to share his experience and expertise. Okay.
Yeah, I do not know why I cannot see a share option.
So that's wait a minute.
Yeah. Where is the share presentation option?
Yeah.
Okay, I find it. I find it.
Yeah. Okay.
Okay. Can you see my presentation now?
It just appear 1 second and then disappear.
I hope you can see now.
I mean, I can't see.
Yeah.
You can't see
But-
now. Okay. Okay. Let me fix the issue. Oh yeah. I think now you can see.
Still no. Now it is happening. Now we can see you have started sharing screen.
Okay. Okay. Thank you.
But it says double click to enter full screen mode. Yeah, perfect.
Yeah.
Oh, it's working now.
Yeah. Okay. I hope you can see now.
Yeah.
Thank you for inviting me in this very timely conference on solar especially in Southeast and Southeast Asian countries. So the topic I am trying to cover in this session is the technical and operational strategies that are required for most of the South and Southeast Asian project developers. So I will try to share some of my experience and perspective while designing and developing projects in Bangladesh and as well as in the regions. So I will try to show first a map. I mean, if you look at the map of South and Southeast Asia, you can see the climate-induced vulnerabilities in many of these countries. And you see the hottest spot where most of the cyclonic surge are bashing, as well as not only cyclonic surge in the coastal zone, but also in the mainland. Many of these countries are prone to flash flood and different type of cascading disasters risk, as well as droughts, salinity, flooding intrusion, and so many other climate related adversities. So these adversities are really posing a lot of challenges to the designer, project developers, as well as the policymakers, especially how to address the resilience as well as future, sustainability of the solar renewable energy venture. So if I just show like Asia's solar boom, which is every year we are having more than 50 gigawatt of capacity coming in our grid systems, as well as in the distributed side of the solar development, which means almost 5,000 megawatt of the capacity every year coming. And as I just mentioned, according to World Meteorological Organization, so most of these Asia's countries are very disaster hit regions. And during the period of 2019 to 2023, 82 million people were affected by the weather-related disasters. And I can also give you an example of the damage level from the cyclonic heat of Mocha back in 2023, which actually caused more than 15 megawatt of distributed solar damage in Bangladesh and to some areas of Myanmar, mostly solar home systems, solar irrigation, water systems, and other form of solar electrifications scheme like solar community solutions and solar street light solutions and some solar photovoltaic, agri-photovoltaic solutions. So the challenges are pretty, common, mostly cyclonic winds, flooding, heat waves, dust and soil spray. So as you know, like most of the solutions, I'm not talking about right now, the solutions that we installed in the last decade, just cyclonic winds actually is the most structural damages and panel misalignment, and for which yield of the system seriously suffer. And due to flooding, flooding cause a lot of inverter and cabling failures alongside soil erosion. So, and causing a lot of infrastructural uncertainty and operation uncertainty in the systems. And heat waves, as you know, if the temperature rises above 25 degrees centigrade, for every degree centigrade, you are losing almost 0.45% of the yield loss, which means as now some of the countries are extreme heat wave hitting. So for them, it has become a design issue to consider how they combat the extreme heat events, and at the same time they can kind of continue with the desired level of output from the solar power systems. Again, dust and salt spray, as I just mentioned, that accelerated soiling and corrosion also raising a lot of O&M cost, because a lot of cleaning and coating issues are involved for the operational sustainability. So I think these are more or less some common challenges most of these plants are facing right now. These are some of the real life damage cases. So as I just mentioned about some of the coastal mini grids where panel misalignment and racking collapse happen post cyclone. In Vietnam, there are instances where huge flooding actually caused many of the inverter goes out of operation for over 3 months and huge downtime created, and that seriously impacts project developers' cash flow. And in Philippines, I think in the rooftop CNI sector, especially in the coastal areas where salt spray corrosion is pretty common, and sometimes it can even cause 25% output loss in up to 3 or 4 years operation time. In India's, I think extreme heat events actually cause a lot of tracker, especially for agrivoltaics, where you need to kind of track the sun movement to optimize the yield of the solar agri-photovoltaic system. So, which also causes a lot of significant yield drop. And as you can see, there are some panels so twisted and damaged because of the hailstorm in many parts of the South Asia. So some of these issues are really belong to how we are designing systems and technically addressing them with merits. Like as I mentioned, most of the systems are designed under 200 km per hour wind speed. So which means if your cyclonic surge going beyond 200 km per hour, which means it can kind of significantly damage your panel racks, which are not even designed to withstand that high wind velocity. And in many cases, what we have seen is inadequate drainage, which is there are not site grading is not done properly, which means the flooding and waterlogging can really damage the inverters, and in many cases they are not even equipped with protective pads, especially for I'm talking about the inverter, because inverter is pretty expensive, and if there are water going inside, it can seriously kind of damage the circuitries that are kept inside for the power conversion. Again, thermal derating. Of course, many of the project developers, they try to kind of meticulously see the derating effect of the temperature above 40 degrees centigrade. But in many cases, just because that requires a lot of that actually implies a lot of cost implications. So that's why the usual tendency is to design something in the range of 30 to 35 degrees centigrades. But when there are events like 40 degree and above, then if those systems are not equipped with the derating, then definitely there are serious yield loss, and you need incremental financing to even address this type of problem. For soiling and corrosion, I think in most cases, the lack of protective coatings and insufficient cleaning, especially in the decentralized areas where dust and soil corrosion is pretty common. So in many cases, what we have seen, there are facilities located in the very remote areas, and there are not enough facilities to clean these type of panel surface and other structures, so that these are actually subject to this type of soiling and corrosion. And again, insufficient monitoring, of course, it augments a lot of maintenance issues. So that is why many cases maintenance is something is very reactive rather than predictive. So and really causing a lot of operational issue. So this table where I try to show some of the innovative solutions that are already in place. Many of the project developers are actually following and implementing some of these measures. Again, we also have to look at some of the solutions from the cost dynamic side, because if you need to adopt those solutions, which means either it have to adjust and accommodate the incremental upfront cost in your capex or in the opex side. So as I can see in the for the cyclonic winds protection, I think some of the solution is like high wind rated mounting structure and dynamic tilt tricking, so that you can have some resilience, like you can prevent structural failure and maintain alignment. So, but for that you need to provision up to 3 to 5% of your capex to actually accommodate this type of solution in your plan. For flooding, I think you need elevated tracking, and for especially floating power photovoltaic solutions, which can also protect electrical and circuitries and extend asset life. For that, you need to also provision around 5 to 8% of the capex. For heat stress, I think bifacial modules and passive coolant can really be an effective solution. And also AI thermal monitoring could play its part. It can also be integrated to the SCADA systems to improve the overall efficiency of the power plants. And for that, you need around 2 to 4% of the capex as upfront investment. For soil corrosion, I think it's some of the very proven solutions are already in markets, like hydrophobic coatings and robotic cleanings and IoT sensors. But for all these solutions, if the size of the plant is reasonable and big, then probably from cost effective side, you can install and you can manage. But for small and decentralized solutions, this is not something like, these all solution you may need to kind of selectively apply and see how it actually reflects in your overall cost structure. So in the O&M optimization side, I think there are a lot of AI-based predictive analytics systems are already in place, like Hail, Smart, and Raptor. Some of these solutions are either drone-based inspections or weather forecast, spatial analysis. Those are pretty much inbuilt in these software systems to monitor not only the events after post-storm, or also can kind of give you an early indication that what level of disasters are coming and how that can impact your asset. So the requirement is something like it's not that big. You can easily recover within 3 to 5 years timeline, but you have to always think that these are like your insurance premiums, so you have to factor those costs in your financial model to gain stronger investor confidence at the end of the day. So this is my last slide, where I put a lot of emphasis on the most of these solutions. If you need to successfully deploy, your O&M team needs to be adequately trained, and these data-driven, and because they need a lot of training and orientation on these data-driven analytics, AI-based analytics, machine learning, and also application of the robotics and drone systems for the post-storm analysis and visual inspection of the damages level. So I think, I mean, for integration with the SCADA systems and IoT sensors, I think this real-time monitoring can play a huge part in the overall operational efficiency improvement. So I already mentioned about the predictive maintenance analytics. So there are tools and systems are already available, but how you are going to apply at what scale, that needs to be adequately assessed before you actually go for this type of systems. And of course, you need to establish emergency procedures in your SOPs so that when there are immediate adversities or climatic events coming, you can easily quickly shut down your system and restart following storms without ensuring minimum damages to your power plant. So I'm stopping here. Then definitely I'll keep myself open for discussing more in the ONM and the other discussion session. Thank you.
Okay, thank you, Mr. Chachis. Last but not least, I would like to invite Mr. Kansa Sakanali to talk about something more futuristic. Okay, yeah, please.
Thanks, Chi. So, can you see
Yeah.
my screen? Perfect.
Yeah.
So, I would actually like to thank Utpal and Dr. Yarimi because they did talk about, energy and data, that decentralized energy system and operations and maintenance. And what the point I wanted to bring is everything is important, but we should also know the data to talk about where is the heat stress, where are the solar panels located, because see, the solar panels are, we are placing them at some point on the earth. Our climatic conditions are very temporal in nature. When we say temporal in nature or spatial in nature, it depends on the time and the space. So the climatic condition of heat stress in Europe would be very different to the climatic condition in sub-Saharan Africa versus South Asia. So how do we then, bring in the geospatial aspect to the planning? So my talk wanted to talk about how do we then bring in AI and earth observation, which meets energy access explorer to map small scale solar. So two things here. Energy access explorer is the energy access explorer is developed by World Sources Institute and in partners in different geographies. So in South Asia we are available in Nepal, and India we are in sub-Saharan Africa in 23 geographies. So it's a world's first digital public good on SDG 7. So digital public good is basically, it's a tag given by Digital Public Good Alliance, and it tells you that these are the open source, open access tool which can be used, and they come to a particular sustainable development goal. So we look at energy planning as a whole. And before I go to that, I wanted to talk about energy planning. So whatever we are discussing today is about energy planning, be it in terms of operations and maintenance, be it in terms of decentralized energy system. So we need to ensure that energy supply and demand are matching with each other so that the solutions are viable for the consumers as well as for the utilities or, the production. So like Dr. Yareme talked about reducing T&D or reducing operations cost. So can we then talk about energy planning? So, okay, I'll just go to the next slide so that I'm not confusing. So currently, if we talk about the global status, we have more than 666 million people who do not have access to electricity. 2.1 billion are actually cooking without clean cooking. And globally, when we say that, total energy consumption is around 17.9% from renewables. And there is, lots of investment coming in. But do we know where these renewables are exactly located? Because these renewables are small in size as you see the whole globe. So it's also important to identify the location so that the solutions we are proposing are local to the geography. So if you're talking about heat stress, it is very hyper local. So can we actually check with the temperature there that this is our solar panel? So the solutions are going forward. And this is the topic of my call session today. So then why actually data matters? Because if we don't have the data, it's if planners or developers do not have data which buildings are powered by solar, or where are the solar plants located, how can we plan their expansion to serve the underserved and unserved communities, be it anywhere? So that is very important for us to talk about data. So then secondly, most of the governments today, we have, we say that the government has invested X amount of money, there is 16 gigawatt of solar globally, but where is exactly it is located, which is not there. And because of that, it is very difficult to uh, track the progress which is going on. And sometimes what happens is, like, because we don't have granular data, it leads to blind spots, and you have overlapping investment, or multiple people are coming in at same place, or there's a very good potential which then get missed out because we do not have access to the data. So what we are saying is, let's map small scale solar. So because we visualize where solar is already deployed, and we are saying small scale home solar system at what a data set, then which can help you adopt trends, how it is happening in urban, rural, in different income groups or different types of buildings, how much of the solar is coming in residential building, commercial building, or and then track progress. Because when we're talking about operations and maintenance, we're talking about resilience, we our climatic conditions, knowing where it is will help us plan. And then it also will support in planning integrated energy planning. I talked about integrated planning so that your demand and supply are matching with each other, and energy is multidimensional. So when you're talking about integrated, you're going to involve climatic parameters, what is the heat stress, if this is area which gets flooding. So like Utpal mentioned, that you will have an elevated platform for when you're doing implementation. So you have to map what is available, where can it be put, and then it can help you support the targeted interventions. So the question is, how do we map at scale? For this particular case, I'm going to take example of Kenya. So if you see this is the map of Kenya, which shows that how much of the percentage of people have solar potential. And if you'll see this block which we have, it's called a Kilifi County, which says that 20% of the county has solar installed. But this is at very high level. We do not know where it is granularly. So while this data shows that, it is available, but where? So how do you do inclusive planning? How do you ensure that you're talking about the needs of health, schools, education, climatic vulnerability, to have more inclusive and integrated planning? So what we did, we decided to automate the solar rooftop detection. So if you see on the left side, these are the buildings which are available, and it has more than 12.14 million building households. Imagine manually mapping each and every solar rooftop. It's going to be very, very resource and time intensive. So can we use artificial intelligence, machine learning with Earth observation to actually, map it at a much faster scale, and then it reduces our intensivity. So what we did, we actually used YOLOV model, which is you look only once model, for object detection. So we are detecting the objects, basically solar panel, and then we use high resolution satellite imagery. When we say high resolution, it is 60 centimeter data we have used. Why 60 centimeter? Because when you see a size of a panel, a 1 kilowatt system would be somewhere around 1.1 into 1.2 or 1.3 size. So you need to have a very high resolution data wherein you can actually go and identify that this particular data is this particular image or infrastructure is a solar panel. So we decided to do it automated. How we did it was, we collected high resolution satellite data. Then we went and labeled them manually, identified these are the panels. So basically you identify these are the panels on the rooftop to actually train the data, because you can do it for some, but doing it for a lot is difficult. And then for your own geography, we divide into small chunks so that it's easier to run the model, train it, and then we train the model because you got the data to tell how it looks like. And then we started training that this is how you do training, and then we started testing the model. When you test the model, you do what is accuracy. If my algorithm says this is a solar panel, is this actually a solar panel? It's not a solar panel. And then when you got the data, you actually created a digital map so that this can be used for further processing. One thing is to have the data, but the data should be then used for a data informed process or a data driven process, which then goes for planning and more integration. Okay, I'll go to the next one. So when we talked about high resolution satellite data, so we collected data at 60 centimeter resolution, and this is the data from Google. We did try open access a source like Sentinel 10-meter, and the reason we wanted to go for open access data was also because we want a open source and scalable algorithm. Because the idea is solar panels are, keep on coming up, and the governments are also supporting it a lot. So how do we build a scalable model and use open access data so that you don't have to, rely on proprietary software, you don't have to rely on you don't have to procure the satellite data. But then because we realized that it is not suitable, like I mentioned, because open access data is a 10-meter by 10-meter resolution, while our solar panel will be around 1.2 to 1.6-meter resolution. So how do you make it more suitable? Then we realized that Google Maps has a good data. I mean, there is Mixar, there is not ESA's data, but we took Google Map for higher accuracy because open access data was not sufficient. But when we got the data, we also enhance the quality. We remove the noise, we improve the resolution, we reduce the blur so that it's easier to identify which is the data. Then comes the labeling and segmentation. So for the code to understand which is solar panel, we actually told them, okay, this is the solar panel, this is how solar panel looks like. And because we wanted it to be open access and open scalable, we did transformations like, you rotate the solar panel in different directions, you try to flip it, because not everywhere south west facing will be the same, and you would like to have the solar, so you should be able to figure out at the different angles or different transformations how solar looks like, because globally it's not going to follow the similar uh, methodology. Then we divided the satellite data into smaller tiles, small pieces, because a big piece, it makes it more complicated for the program to run. And then we worked on improving the model by, having multiple types of rooftop or the panel configuration, because everywhere, every geography, every country, the panels are different. And then the idea was to reduce the processing load by by segmenting the image. So what we did is, then when we trained the model, that you use the model, and then if you'll see, this is how we did it. So this was the image we used, and then this is the data which was ground truthed, and what was the prediction done by the model. So the idea was that the model actually is able to improve over the time, and we received a 94% accuracy when we did different kinds of tests. We evaluated against precision, recall, and different scores. So basically, how precise is the output? And recall means that, did we actually go back and check if it is right or wrong? And then we did validated using the ground truth data, which we got it from Google Earth Engine, to just see that, it has a high precision, and then it has a strong detail in actually telling this is a real solar panel. And but then, like I mentioned, that, the work doesn't stop there. So we created a map. First thing is to actually identify the panel. And then once your model is working correctly, you then train the model to expand it for the whole geography. So we did it for Kilifi South, which is a county in Kenya. And then we fine-tuned the model to improve across the lighting condition. If the rooftop is different, oriented differently, the panel size might be different. And the code was able to identify 274 rooftops, which are there for the small home system. But then I said that, like we said, the rooftops in itself is not important. It has to lead to roadmaps. So what we did was, this outputs of the model, we had integrated into Energy Access Explorer, which is again, which takes the multidimensionality of energy into and energy for energy planning. We have, we then get the data on energy demand, what is the demand which is coming up from your population, from different social and productive loads. And you can use the models like ramp, you can use models like onset to actually estimate the demand for irrigation, demand for healthcare, demand for electric vehicles. Then we talked about what is the potential of solar, what is the amount of sunlight coming, and then what are the socioeconomics, to have strengthened a data informed planning, which is inclusive and integrated in nature. And then the idea was that, how do you enable high resolution and inclusive planning? And because the way we have worked and developed the code is, it is modular and open source. So the idea is, going further, we are going to expand it to South Asia and Africa. because then we are able to support what is the current solar deployment and what is the solar future application coming in. So now you get, these are my buildings which have solar present, and these are my buildings which do not have a solar present, and this is the installation potential, and these are the buildings which actually are lying in high heat stress area, or these are the areas which gets flooding. So how do you then have a integrated planning? And the idea was that, when you are able to map where solar is deployed today, you can think of tomorrow and have more integrated and inclusive decision for the energy systems which are there tomorrow. I'll stop here, and I give this control back to you.
Okay, thanks, Ms. Sakalali. Before I open the floor, the discussion to the floor, I would like to take the privilege of moderator to ask the first question to the panels. So I come from the energy industry or power industry. So my understanding, several cultures such as the prudent, cost conscious, and focusing on a lot of reliability issue in the DNA of the power utility people as well as the regulators. So from your perspective or from your experience, how can we address these kind of cultures such that we can expedite the implementation of the technological solution to enhance our solar energy deployment in the Asia Pacific region? Anyone has something to share? Anyone?
Sorry, I think my internet was a bit choppy for some time. Can you please repeat your question again?
Oh, sorry. Yeah. My question is that I think I come from the energy industry or power industry. So my understanding, the culture, deeply in their culture is for example, some kind of practice as reliability, cost, and maybe the proven solution and so on. So now when we are talking about some innovative technological solution, the power utility people or energy utility people or the regulator may have a lot of hesitation. So from your experience or from your knowledge, so or your insight, how can we address this very cultural issue in the industry, energy industry, such that we can expedite the implementation of all these technological solutions to benefit the solar industry?
Can I share my experience if you allow?
Sorry, yeah, you want to share?
Can I share my experience if you allow?
Yeah.
Okay, so no, it's a great question. Actually, what we discussed for all this innovative solution, as I just mentioned, that in many countries and in many cases, the uptake of this solution are still very limited. Especially in many of the grid connected systems, those are installed like 5-10 years back, that is still struggling in many cases with the low yielding issue, as well as they're struggling to kind of address the post-storm recoveries, and an incremental investment is another things they need to kind of adjust and accommodate in their cash flow. So I think there is a kind of adoption rate for all these sustainable and innovative solutions. But the rate is higher in most of the advanced countries than in the middle income and low economic developed countries. And at the same time, when there are very competitive tariff situation exists, especially in countries like India and Bangladesh, and in many African countries that Akanksha mentioned, putting all this innovative solution actually might take them out of the competitive landscape. So they need to come up with a very rational solution. And first, they need to remain in the competitive range, what they are actually offering to the utility, so that they can have a long-term offtake agreement in place. Otherwise, so that is why, where in the most disaster-prone areas, utility need to come up with some special consideration for all these power plant. If they are not equipped with these solutions and predictive and all these data-driven solutions, the long-term stability of the plant will be at stake. So I'm stopping here, then definitely my other fellow colleagues will actually give more lights on it.
I can go next. Thanks, Utpal. So I also feel pilots have been very successful. If we are taking a small pilot and try unable to succeed it properly, it brings in the trust of the partners, and it has to be a co-created solution. Even when you go to a utility, it cannot be that Utpal is going and saying that I'm from Asia Clean Partners and this is the way or I'm going and saying, oh, WR Idols. It all have to be co-created. So we go with the utilities, we go with the developers and say, this is what we can bring together. Let's have a pilot together so that you can actually implement it, see the results on the ground, and then figure out what is the financing which can help them support and take it forward. And secondly, what we have done and we have realized for one of our work is economies of scale. So if you're able to aggregate the demand of say solar, so if you're putting a solar, and this is one of the papers we did recently, we used the machine learning to understand what is the solar installation potential, aggregated the demand for a SME cluster or small medium enterprise. And with demand aggregation, what happened is they were able to get better bargaining power. Their O&M was considered better, and then ROI reduced to 4.1 year from 7 years. So then you have to bring in multiple dimensions. You have to do pilot, you have to do a lot of capacity building to make them understand why this technology has been useful, and then bring in economies of scale once the pilot is successful. Everything has to be done in a co-creation manner, and that we are partners and we are coming together to do it, not like somebody is coming and saying this is the best way for any geography.
Okay, if I may, yes, as I mentioned, that hardware can reduce cost as what happened in the solar power, the solar panel. But then that the soft cost or this installation or the integration of different parts of technology, that might be not so easy to reduce the cost. So we need to have a kind of many attempts to try to implement some small scale project through regulatory sandbox, for example, because the energy sector can be heavily regulated depending on the country context. But then that we really need to have kind of testing, experiment, and learning, and the shared experience so that we can learn together, so that we can somehow try to have more kind of standardization also in the software parts, soft parts of the technology.
Okay, thanks for the panel for their sharing. So let me pick one of the question I think is interesting. The question is about it just disappeared. So the question is about in most climate vulnerable countries of South and Southeast Asia, factor in both technical solutions and associated costs to combat climate-induced climatities is becoming critically important, not just to strengthen the reliability, but to ensure the long-term business viability of the ventures. So any comment on this?
I think this is what is the central theme of today's session. I mean, what we are actually talking is not only kind of, bringing up some solutions and showing their merits and characterizations, but also we are telling actually how those can be applied to actually have better safeguard against all these climate-induced adversities. So, and at the same time, when we are only thinking about the resilience and the stress, but at the same time, we are also telling that for ensuring the sustainable production or yield from these solar power plants, because many of these project developers, they are very tightly bound with the utility for delivering power at some specified manner, and their power purchase agreement is contractually very tight. So if they lose on the yield side without all these backstopping support, probably they will be in a in a more disadvantageous side, and they will not be able to kind of get the required investment recovery or ROI from their intervention. So from both climatic side, from the resilience side, and the sustainability side, I think it's important that we factor all these cost upfront investments very diligently in the project planning phase.
Okay, thanks. So in view of time, so I have to reluctantly to stop the this section. But before I close this section, first of all, I would like to really thank our speaker for their very insightful sharing. In particular, Dr. Yarami give us a very holistic view of different technological solution from distributed to centralized context. And then Mr. Bhattacharjee, you show us we need to down to the earth, okay, look at both the solution and the cost, okay. But probably I think we need to address something that how can we translate the increased capex into better performance, okay? And then Mr. Sakalari, you give us a very innovative way to make use of AI in the solar industry. Hopefully, I think in the future we can see more and more AI application in the solar industry to help us to expand the application or penetration of solar energy in our society. Okay, really appreciate and thank you all. Okay,
Thank you, Sisi,
so,
for inviting us.
Thank you so much.
Take care.
okay, bye bye. Take care.
Bye.
Bye bye.